All right, welcome to our overview video of the procedure sections for Lab 1, Week 2. This will be brief because embedded within these sections are links to other videos, tutorial videos, that show you how to do the various tasks in much greater detail. I'm just going to briefly summarize what the tasks are. So let's slide down to Week 2. The first task is planet and dwarf planet images. So in Week 1, you took a lot of pictures of planets and dwarf planets. So we come here, and the first link we encounter is Afterglow Access. This is our image analysis system. You'll log into it using your Skynet credentials. And there's another link to a tutorial that will show you how to adjust the brightness and contrast levels in these images that you took to bring out details in them. Then you're instructed for each of the planets you observed and for the dwarf planet series, which is between Mars and Jupiter. You will use Afterglow to zoom into your object and zoom way in, fill the entire screen with your object, and then adjust the brightness and contrast levels to bring out as much detail as possible. Don't worry about trying to see the moons in this section. Just focus on the surface detail of the world. Some worlds will have detail, other worlds won't. So see what you can do and then save your images. Now here's an example, just to set your expectations. This is a picture of Mars that I took when Mars was pretty close to Earth, about as close as it can get. And this is what Mars really looked like at that time. You have to remember, you're observing with a small telescope from the surface of the Earth through Earth's atmosphere and then all the way through space to Mars. And so this is the kind of image you can expect given those circumstances. Now, if you're in space or if you're in orbit around Mars, this is what you get. And you've seen lots of pictures of Mars, and these pictures are usually pictures that were taken with the Hubble Space Telescope or from satellites in orbit around Mars. You're not going to be able to achieve that kind of quality from the ground looking through Earth's atmosphere. But you can see some things. Like here I see the ice cap. It matches up here. Dark regions match with dark regions, light regions with light regions. You can see some detail, especially with planets like Jupiter and Saturn that are very large from an angular point of view, and also Venus. You should be able to discern the phase of Venus fairly well. Anyway, once you've done this, you'll upload your files here, and then describe any detail you see in these images here, in each of the images. Describe the detail. Okay, let's take a look at the next section. Here, you're going to learn how to make some basic measurements. In particular, you're going to learn how to measure the angular sizes or the angular diameters of the worlds that you just worked on in the previous section. So there are two tutorials here. The first tutorial is very short, and it shows you how to figure out what telescope took your observation and when it took your observation. The second tutorial shows you how to measure the angular diameter of your world. So then you're instructed for all those objects that you just worked on in the previous section, adjust the brightness and contrast to bright target so the planet is not washed out, and then measure its angular diameter to the nearest 0.1 arc seconds, and you'll include that in the table down here below. Now, a couple notes. For Saturn, we're going to measure the angular diameter of its rings, not the planet itself. And if the planet is in a phase, like Venus often will be, you're going to measure from tip to tip, not the short distance, but the long distance. You then input this information into this table. First, indicate whether the object is currently observable. Not all objects are, as we've discussed before. Some may be too close to the sun. And for the ones that are observable, indicate which telescope took the image for you, when it took the image, month, day, year, hour, minute, second in universal time, and your measurement of the angular diameter goes here in arc seconds. Then you want to sign your name to attest to the fact that you yourself collected these data and took these measurements. Kind of an honor code pledge. Now in the next section, we're going to use a program called Stellarium to check these measurements you just made. Here's the link to get Stellarium. What Stellarium is it's planetarium software, free, downloadable, that works on your computer. And we'll use it both in this lab and in other labs. You can see here it works under a wide variety of operating systems. So pick whichever is appropriate for you, install it on your machine. And if you encounter any technical problems with it, you can always come back here and download one version back. That usually solves such problems. In this next tutorial, we'll show you the basics on how to use Stellarium. And basically, you're going to use Stellarium to simulate the sky at the exact date and time that Skynet took your image for you, for each of your images. After watching the tutorial, we have a few reminders. The first is to make sure Stellarium is in universal time, because those are the times that you recorded for when Skynet took your images. You'll also want to turn daylight saving time off. In the Stellarium simulation, you'll want to turn off the ground and the atmosphere, so you're just looking at space and the objects in it. And then you'll want to change Stellarium's date and time to the date and time that Skynet took your image. Then you can zoom into the world and you can read off the true angular diameter of that world. And you'll want to record that to the nearest 0.1 arc seconds in this data table right here. Now there's just one note. Again, with Saturn, we're measuring the angular diameter of its rings. So you want to make sure you read off the correct value. For Saturn, use the value for the rings. For all the other worlds, you just want the angular diameter of the world. Once you have these, you'll calculate percent errors. And here's the equation for percent error. The measured value minus the true value. And then you take the absolute value of that difference, the positive value of that difference, divide by the true value, and multiply by 100%. Coming down here, we have another box where you sign your name to attest to the fact that you collected that data yourself. In this box, you're going to take your first percent error calculation in this table and present it, so a sample calculation. And then you're going to discuss sources of error. In particular, I want you to think about atmospheric blurring. As the light comes in through the atmosphere, it gets blurred out by about an arc second. Now, for worlds like Jupiter and Saturn, which are 30, 40, 50, 60 arc seconds across, an additional arc second of blurring is not that big of a deal. But for small worlds, such as Ceres, which is less than an arc second across, an arc second of blurring is a huge deal and will lead to a very large percent error. So frame your discussion around this effect. Now, both in this lab and in future labs, when discussing sources of error, try to avoid the phrases human error, measurement error, calculation error. None of those are valid sources of error because those are things you could fix. If you know you made a calculation error, you should go back and recalculate it. If you're having problems, then you'll want to talk to your instructor and he or she can guide you through a proper sources of error discussion. Okay, in this next section, you're going to identify moons in your images. And for this, we're going to use that second set of images you took of the gas giants, the ones where you use different filters that let more light through so we can see more of the faint moons in orbit around them. In this section, you'll use both Afterglow and Stellarium in concert to identify the moons in your images. With Afterglow, you'll adjust the brightness and contrast to bring out as many moons as possible. With Stellarium, you'll simulate the sky at the exact date and time that Skynet took your image. Here is a link to a tutorial that will show you how to do all of that. It will also show you how to mark and label objects in your images. After watching the tutorial, we have a few reminders. You'll want to make sure Stellarium is in universal time. You want to make sure the ground and the atmosphere are turned off in the simulation. And you want to change Stellarium's date and time to the date and time that Skynet acquired your image. Then you can zoom into the planet, and you'll want to change the orientation in Stellarium to equatorial mode. We show you how to do that in the tutorial. And once you do that, your image in the simulation should be lined up. If they aren't, you may need to rotate or flip your image in Afterglow. But after that, they should be lined up. You should be able to identify which is which, such as this moon here is Titania, this moon here is Oberon, this moon here is Umbriel. Now, one thing to keep in mind is that with the real image, the light from Uranus, planets are bright, and so in this case with Uranus, its light gets scattered over a larger region than you have here in the simulation. And some close-in moons may be lost in what we call the sky glow. Now you can play with this in Afterglow, changing the brightness and contrast, trying to pull an extra moon or two out of the sky glow. But some moons might be lost in it, and there's nothing you can do about that. Now a couple notes. If you don't see any moons in your image, then there's probably thin clouds blocking some of the light, and you may need to reshoot that image. Also, students sometimes have difficulty finding Triton, Neptune's large moon, the only moon around Neptune that you can see. It's the point of light that's right next to Neptune in your image, close in. Now, for the moons that you identify, what you'll want to do is zoom in to the planetary system, mark and label each of these moons, and save that image as a JPEG file. Once you've done that, you can upload those images here. Also, you'll want to enter the universal date and time that those images were acquired. For each moon that you did find in your images, you should Google that moon and enter one fact that you've learned about that moon in this box here. Okay, in the next section, we're going to look at the dwarf planet images. You acquired images of Ceres in the asteroid belt, but also Pluto, Haumea, Makemake, out beyond Neptune, at least those that were observable when you did the lab. In this tutorial, you'll learn how to take those images and compare them to archival images taken long ago, something called the Digitized Sky Survey, and you'll learn how to line them up, your image and the archival image. You'll mark identical stars in both images. But the dwarf planet will only be in your image because it's moving across the sky and it wasn't in this same location when the archival image was taken decades ago. So by marking similar stars in each image, you'll find the one point of light that's in your image that's not in the other, and that will be the dwarf planet. And you'll want to mark and label that. And then you'll upload both your image and the DSS image, marked and labeled, into WebAssign here. In this box down here, you'll want to Google one fact about each dwarf planet that you found in your image. And then that takes us to our final section, which is pretty straightforward. These are the deep sky objects and also the image you took of Earth's moon. You want to put them into Afterglow, adjust the brightness and contrast to bring out as much detail and as much structure as you can. You'll upload these here, and then you can Google a fact about each of these objects and present that in this box. Okay, that's the end of this overview video.